in conducting a geospatial impact evaluation. And the impact evaluation in question is this one. And it's also a chapter in the geospatial impact evaluation textbook. And it's intended as like a kind of practical chapter with code that readers can download, just like you're doing now, basically, and replicate. Okay, well, that's loading. Basically, this exercise, the chapter and the paper it's based on, it evaluates whether a major industrial mine has managed to compensate for its impacts on forest cover through biodiversity offsetting. Excuse me? This is not working. Okay. So I'm going to give you a quick introduction. Then we're going to run through the exercise that's kind of split into 5 different parts. And I'm going to walk through the components of the code in each part. And I think it's probably best if you just kind of run it simultaneously because it runs quickly and then we can discuss the outputs and how to interpret them. So this, I have no idea what sort of level you guys are at. Like this could be completely easy peasy, in which case you can make it more complicated if you like, or it could be completely new, in which case hopefully this is a clearly explained introduction. So very briefly, geospatial impact evaluation is very well suited to evaluating forest cover change. And that's partly because there's good data availability monitoring forest cover. You know, you can monitor deforestation from space. There's data that's available kind of since the mid-1990s, since the 2000s, every year. And there's different data sets that you can choose from to kind of best suit your purposes. Forest conservation and restoration is a major focus of environmental policy. And there's been various kind of policies and projects that are implemented in specific places that have well-defined boundaries. So things like protected areas, you might get payment schemes that are implemented in households or municipalities or whatever. So yeah, projects are applied to specific areas, with some areas getting treatment and others not. But there are challenges. Some of them have been kind of discussed more in detail in earlier sessions, but choosing an appropriate control is one of the major challenges, because when you're looking at, let's say, forest conservation projects, the area they are applied to is very clear, but the areas that don't receive the treatment, there's no like well-defined control areas, right? It's not like if you're implementing a economic policy to some districts and other districts don't get it. Then you can use your other districts as your control, and that's nice and clear. With these sorts of programs, it's not like that. You don't get like non-protected polygons. Also, land systems are very complex, and the factors that influence deforestation, many different factors can influence decisions on how people use land, whether the forest is conserved or whether it's converted for other uses. And that can make it quite difficult to not only identify confounding factors, but also to find data that controls for them. And measuring reforestation as an outcome is very difficult. You can ask me about that later and I'll complain about it for ages. But luckily in this study, we're looking at deforestation, which is much more straightforward. So the case study that we're going to be looking at today is this one in Madagascar. And basically, We're looking at the question is whether a major infrastructure development has managed to offset its impact on forests. And the infrastructure development in question is the Ambatavi nickel and cobalt mine in Madagascar. This mine started production in 2007. It was constructed in 2007, and it's located in primary rainforest, or was primary rainforest, now it's a mine, but at the southern edge of a protected area, in one of the largest remaining fragments of kind of primary rainforest in Madagascar. And to access the deposits, the company had to clear over 2,000 hectares of forest, really good quality primary forest. And this was kind of in the early 2000s. And the company was very well aware of the reputational risks that would come with that. And it also wanted to try and position itself as like a leader in sustainable mining. So the company committed to offset the biodiversity loss associated with this clearance of forest in order to achieve no net loss of biodiversity. And in this impact evaluation I did during my PhD, we used geospatial impact evaluation methods to evaluate whether the company was on track to achieve no net loss of forest. And yeah, our findings, which I'm not going to tell you now because I want you to calculate them, they attracted some media attention, which was very cool. So, in order to offset biodiversity loss, the company designated 4 biodiversity offset sites. This is the mining footprint. This is one of them. This is the second, and then the 4th one's up here. Okay. And in these sites, in combination with local NGO partners and international NGOs, they implemented conservation activities and land use restrictions to try and slow deforestation, which in this region is mostly driven by shifting agriculture. The offsets had staggered implementation. This one was kind of officially protected in 2009, and the last one was protected in 2014. So we used matching, pixel-based matching and differences to estimate the counterfactual deforestation within these sites, and then compare the counterfactual, what would have happened if these areas hadn't been protected, to what actually did happen. And from that, we infer the impact of the protection. We also did, I think, well, at the time, I thought they were very extensive robustness checks. Now I think they're actually quite standard in some fields, but they weren't so standard in conservation when I did them. And also, this was a cool thing that happened last year. These results have been independently checked and verified using different data and different modeling choices, and the results are robust. But you are going to replicate some of these later on. So, aims and learning objectives. We're going to understand the key steps and decisions involved in conducting an impact evaluation of policies aiming to slow deforestation. We're going to replicate the key analytical steps of this in R. We're going to learn how to test the key assumptions, so the parallel pre-trends. And we're going to test the robustness of results to alternative matching specifications. We're going to assess and interpret the results at each stage. And then hopefully, for the newbies in the room, you'll gain confidence in applying these tools and methods to your own work. So today, because we're time limited, we can't replicate the whole GIE workflow. So we're just going to focus on the impact evaluation part. We're going to do the matching, the site-based differences. So I did the DIDs individually for each site because I only had 4 sites. But then I also did a fixed effects panel regression, combining the data for all sites. We're going to do both of those. And then we're going to run some robustness checks. In the paper, I did 116 different matching specifications, but we're going to do 16 because we don't have very much time. But this, this is just almost the tip of the iceberg of the effort that goes into doing a GIE. Because before this, I did all of this, which is the data selection and preparation. So first of all, I had to define the outcome variable. I'm about to be committed to offset biodiversity loss, but we measure deforestation. Basically because we just didn't have but biodiversity is really, really difficult to quantify and to analyze. And we didn't have the biodiversity data over a sufficient time period for the treated and the control units. Doesn't exist. So we use forest cover as a proxy, which in the setting, most of the biodiversity lives in the forest. So it's an imperfect proxy, but I think it's a decent one. We use the Hansen et al. Data, the global forest change data. If I was to do this again, I'd probably use the tropical moist forest data because that is able to capture regrowth, which I think is more appropriate for this context where shifting cultivation is really prevalent. But it wasn't available when I was doing this study. So use Hansen instead. But I mapped it to a national forest cover map of Madagascar in 2000. Because basically looking at the data, I think there's loads of false positives in the Hansen data. And by masking it to the national data, it removes a lot of questionable deforestation detections. And this is, I was following someone else in that decision. But anyway, it's something to consider. Like, can you make the available data better by combining it with other data that you think is perhaps more reliable? Because we use that data, our unit of observation is the 30-meter per pixel, but our unit of analysis is the offset sites. And this may seem a bit like semantic now, but I think it makes more sense a bit later on when we start to work with the data and manage it. And also because the intervention was applied at the level of the offset sites. And the question is whether the conservation protection reduced deforestation within these sites. Did it reduce it, and if so, by how much? It's not, oh, did it stop this 30-meter pixel getting cleared? The control area is we set as this whole province or X province. And so we sample pixels from this province that were forested at baseline in 2000, outside protected areas, and outside the 10-kilometer buffer zone around the offsets to try and make sure that our control sample is not impacted by spillovers. And because of those choices, because there's no non-offset polygons, we had to use pixels, like pixel matching. And so then we collected our data on confounding factors or other variables that are important to control for. And we sampled those values we used a grid-based sampling strategy to select pixels so that we're not using all of the pixels because that would be huge. So yeah, we sample pixels that are 120 meters apart from each other. And then we extract the values of all of these environmental covariates, geographic covariates at those points. So yeah, it took me a while to explain all those previous steps because there are lots of steps before you even get to like the impact evaluation part. And all of those steps, you have to make lots of decisions on them and it takes ages. And you had to make sure those decisions are kind of justifiable.
Sorry, can I ask a question?
Yeah, please.
Maybe I missed it, but how deforestation is context is defined?
Stand, replacement, clearance of forest.
So you have the cooler map, and then there's this like the class changes.
Mhm. Yeah, and it's irreversible. So once a pixel is cleared of forest, it basically drops out of the analysis because I use the Hansen data.
Alright.
Just another question.
Yeah.
Maybe just to understand the 30-meter pixel is the selection. You come from Landsat, it's why it's 30-meter. And in case it's Landsat, the satellite measure, like, just to ask why it's not something like this and just.
Oh, because we needed a long time series.
So okay, for time.
From 2000. Okay, so then you get a data set that looks like a much longer version of this. The rows represent sample pixels. These are the environmental covariates. But this is an important thing actually that I will talk about later. The tree loss is our outcome variable. And because it's Hansen, 0 means that there was no deforestation. And because I made sure that all my pixels were forest cover in 2000, if they've got a 0, it means that they're still forest cover in 2020. Yeah. And if it's a value between 1 and 18, that represents the year the pixel was cleared. And then treated is a binary indicator about whether it's in the offset or in the control. So that's enough of me just blabbing at you. Hopefully it won't look like this. So, have you all got the R markdown ready to go? Perhaps you guys can look at this lady's computer.
That's the script underscore biodiversity underscore offset.
Is it?
I'm wondering, I don't know.
No, it's offsetting deforestation workshop.
Oh, okay. Oh, thank you.
Have you got it?
Yep.
Okay, great. So we're gonna start at the top. There's a lot of text because I don't know why really. But if you scroll straight down to line 114, first of all, we need to start by loading the libraries. Now you might need to install these packages if you haven't got them already. Does anyone not know how to install packages? Does anyone need any help?
I'm kind of like automatically suggesting the installation of that, so I'll just put.
Yes. Okay. Okay. So the quickest way to do it is to open the file that we downloaded the experiments. And if you open that file, it should automatically load out the script. Yeah. Can you get back to the file that you downloaded, please? Let's see what this works. Just for that. Okay. If you go back to that if you download the whole folder, you could download it like this. Because the folder is contained pages files, the folder should do file. Yeah. Maybe close this version. Okay. So this should be in a folder, and I think the folder contains the script. Yeah, I think so. So if you go back to that bit of site, that's exactly yes, okay, yeah. Yeah, so now from here, try to look at your list. And then if that doesn't work, you can manually load that dot. Or choose another one again. I'm sorry. You might just have to either watch this or check out that. Okay, so we've all loaded the libraries, right? Next step is to go. We need to do some data cleaning. So if you run the next step, which starts on line 137, this will load the input data, which is this data sets look like that for both the treated area and the control. And I should say that we're going to do this, the difference in difference analysis, just for one offset, which is called Ankarana. For reasons, and the reason why I've selected that, you will find out later. So yeah, this step, it's a bit boring, but it basically just renames the columns into things that make sense, gets rid of unnecessary columns, and gets rid of NA observations, missing data. We all done that? Cool. Then we pre-filter the data to remove control pixels with values in any of our 5 essential covariates that are way outside the range of the treated sample. So basically we're saying that if an observation has a value in any of these 5 covariates that is greater, that is the standard deviation plus the maximum value in the treated sample, it's just way different and it's never going to be matched, so we get rid of them. And this has, before I did this, I was really struggling with the matching. Like, the balance was rubbish, it just wasn't working. After I did this, basically it reduces the spread of the data, and by doing so, it makes the calipers that you use in the matching much more restrictive. So it's good in that respect. And doing that reduces the size of the control data from 600,000 observations to just 200,000. Have we all done that step?
No, what is caliber? Whatever you have, it's like visualizing and putting the table.
Yeah. And the caliper is what we use in matching, which I can talk about a bit more in a second. But it's not going to harm your analysis because it's getting rid of observations that are just completely different.
Because you also have a big potential for observing matching, because you are drawing in some method changes.
Yeah.
then do the matching.
Yeah.
So probably this.
Yes, that's one question. Yeah, and also I can do this because I've got a massive control data set because I sampled from the whole region. So next step, run the next bit, please. We've just finished. Yeah, we just finished 237.
Yeah.
And then there's just a little added subsection. If you could just run that, which is 246 to 250. And then once you've done that, that's the like boring data preparation bit over. And now we can go to the fun part, which is the start of the matching. So we've got, oh, I should have run this myself, actually. We've got 2,862 observations from the offset. And we've got nearly 200,000 observations from the control area. In the next step, we want to make sure that the comparison sample is a good comparison, that we're comparing apples for apples, that we're comparing like for like. So we use matching to select a subset of samples from the comparison area that are as similar as possible to the treated sample in these 5 variables that we hypothesize influence the allocation of the treatment, which is the offset protection, and outcomes. Because if we didn't control for these things, any difference in deforestation could be because the comparison sample is just different. It's different to the treated sample and it's got nothing to do with the offset program at all.
Wait, I have a question. And maybe you already mentioned, what is the distance to edge?
Ah.
Of the
Distance to forest edge. And because all of my pixels were forested in 2000, it's like the distance from these forested pixels to the nearest edge of the forest.
okay, so because you made that.
I didn't make it, someone else made it. But it's a raster of distance to it's effectively distance to the nearest non-forest pixel.
Okay,
Yeah. And you might remember that when we looked at this data, there was more than 5 variables, right? There's 10 here. And that's because I was very green and optimistic. And I thought that you could match on 10 variables. Turns out you can't, it's really difficult because you're trying to maximize similarity in loads of different things. So what I did in the end is I selected the 5 that I thought was most important. And I used them for the main matching specification. But I tested whether the other ones were important in the robustness checks. So I kind of iteratively added the other ones in the robustness checks to see if it affected the results. And it did.
yeah, just a question on the selection of controls.
Yeah.
Did you take into consideration of maybe there could be any spillover by user classifications?
Yes, so I didn't sample control for pixels that were within 10 kilometers of an offset boundary. And I also did a spillover analysis where I took pixels from that 10-kilometer buffer zone and I assigned them as treated and I tested whether they were affected by the offsetting intervention. And I found that they weren't, so there was no spillovers. So this is the very nice 2-line code that you can use to run the matching. I use the match it package. I can't remember why. There's lots of different options. And in it, this is saying you specify your variables that you want to control for. Then you specify the matching method. So this is nearest neighbor matching, which says that I want to match, because you're matching comparison to treated. You're saying I want to match a comparison pixel to the closest, not geographically, but like to the treated pixel that has the most similar values. I use Mahalanobis distance. Distance is like that again, that's not geographical distance. It's like the statistical distance. It's the statistical measure that you use to say these two pixels are similar or not. And I chose Mahalanobis because I think it's better at maximizing similarity for individual variables than propensity score. Because propensity score lumps all of the variables together to define like a likelihood of a pixel being in the treated or the comparison. And because it lumps them all together, the pixels might be similar in that likelihood of treatment, but they can still be very different in one or two of the variables. And that's why I use Mahalanobis. But the whole point of this like exercise is that other choices would have been completely fine. I could have stood up here and said, oh, I use propensity score matching or the other one, and it would have been fine. But it's important to see how those things affect your results.
And then you would have just changed it to propensity or
Yeah, could have done.
distance? Okay, just.
Yeah, and it would have been fine. But the important thing is that those choices can have actually, they're all justifiable. None of you would have crucified me if I stood up here and said that, but they could give us a very different result. And studies have shown that like the estimated effects can vary like threefold depending on these choices. So it's really important to check. Okay, so can you run that chunk of code, please, if you haven't already? And oh, I forgot to say about the calipers. Yeah.
So the distance to deforestation would be the closest. How do you map that distance? Because what would be the difference between the distance edge and the distance to deforestation? Because the distance edge is usually
They could be very similar. The distance to deforestation measures deforestation in previous decades. So from 1990 to 2000. Don't ask me what data I used to do that because I can't remember because I did this study like 4 years ago. And maybe should have revised. But they're likely to be similar in some places. But the distance to edge could have been an edge that was established decades ago. Whereas distance to deforestation captures like proximity to more recent pressures. Does that make sense?
Can the edge be water or something? In that?
Yes. Yeah, it's distance to pixel that's not forest. And yeah, just a note on the caliper. The caliper is an important parameter that states the acceptable difference between matched pixels. So you could say if a treated pixel you cannot find a control pixel that is similar within this threshold, which in this case I set as 1 standard deviation. If you can't find a pixel that's similar within 1 standard deviation of the Mahalanobis distance for all of your 5 variables, then it doesn't get matched. So that like prevents imprecise or like it prevents not very good matches.
and what so if you do not set a caliper, what would be the default? Or there is no default.
I can't remember.
But we should always choose the caliper based on our assumption.
I think so.
Okay.
Yeah. And it should. You can set calipers of different sizes. If you set a really strict one, which I would say is 0.25, then you're saying I want the matched pixels to be very similar. But the trade-off is that you might not match lots of pixels, and that can be very bad because if the pixels that aren't matched are all in a certain place that have certain characteristics, you might get bias. So I think the most important thing is a balance, but I think you really need to prioritize matching as many of your treated pixels as possible.
So you want to try with different calipers, and this was like, a good balance for you.
So I tried a few specifications before. So I ran the matching and I compared the balance, which you will do in just a second, before I did any of the regressions, because otherwise that would be very bad. And I chose the one that yielded the best covariate balance, the best of these scores, and matched the most pixels. And it was this one. So now, if you run the next bit of code from lines 285, you'll be able to view the results of the matching. And it will look something like this. So this is basically saying we've got 2,800 treated pixels from the Ankara offset, nearly 200,000 control pixels. After matching, we've still got the same amount of treated pixels, which is really good because we managed to match all of them. And because we matched 1 to 1, we matched one control to one treated, we've got the same amount of control pixels. So that's great. The next table, this shows the comparison between the treated and the control in all of the 5 variables before matching. And the next table shows the comparison after matching. And the columns you want to look at are the third column, which represents standardized mean difference, and the last column, which is new and exciting and didn't exist when I did this, the standardized paired difference. So the standardized mean difference says, in each of these variables, what's the difference on average between the whole treated sample and the matched control pixels? And the kind of threshold, accepted threshold for a good match is 0.2. And you can see that all of these are well below 0.2, which is very good. So that's saying, on average, the two samples are very similar in these variables that we think are important predictors of both the treatment and the outcome that we need to control for. We need them to be really similar in these variables, and they are. But this is a new thing. This says, for each of my matched pairs, treated and control, what's the difference between them in values of these variables? And on average, what is that difference between the two samples? And this is not so good in these two, but it's still hovering around. This is new. I actually don't know whether the 0.2 applies for this.
I think it has to the individual.
It depends on the measure.
Okay, cool. Well, that's excellent. So it's in the units of the output.
Yeah.
Oh. Cool, great. So anyway, the matching was good, is the take-home message from that, yeah.
Right, so in table 2, we are comparing these 100,000 control pixels versus 2,000 pixels, and in table 3, we are comparing 2,800 with 2,800, exactly.
Yeah, exactly.
So the question also quickly about, so each pixel is uniquely matched with another pixel. There is no situation where one control pixel is helping 5 or 3.
Exactly,
No.
yeah.
Did you specify it somewhere in this command that is uniquely matched with one?
This replaced.
Method here, so method here doesn't ensure that the control pixel is also at least one.
Yeah, so there's two commands. There's this replace equals false. And I think that's saying that once you've matched the control, you can't use it again. But there's another one which is ratio, which we'll explore later. And that says, if this is true, and you can use control pixels more than once, how many... No, that's not right. I think that... It says how many control pixels you can match to a treated pixel. But I don't know if that's like, maybe you guys know. Does that mean that every treated pixel is matched to 2 or 5 or 10? Yeah, it does. Okay.
Yeah, it's multiple pairs.
Yeah. But then if you use that, you have to correct for it in the regression, because you could have a control observation appearing multiple times. So at this stage, we're very happy. We've got good matching, and that means we can proceed to our regressions. So you can run this next section, or you can skip it. It doesn't really matter. That's just a way of the next bit of code from line 306 to line 323 basically just kind of extracts the key the key like balance measures and the key checks from the matching into one data frame, which you would need to do if you were doing this for a study, because then you can put it in the SI. So the next thing we have to do is to extract the matched pairs, because we haven't done that yet. So if you could just run the code from line 335 to 340, and you'll see in the environment pane on the right, next to the data set called M data, you'll see that there's 5,724 observations, because that's the 2,800 times 2. And here, if you have matched with replacement or with a ratio greater than 1, then this is where you'll probably need to correct it by setting weights. So for weighting those control pixels that feature more than once. We don't do that for the main matching specification because we don't need to, because it's 1-to-1. Because it's nice to keep things simple when you can.
So what would you do if the previous test was not balanced? Like you see that the back matching is well, they weren't very similar.
Yeah.
What would you do?
Try different specifications.
Okay.
And
also like changing the variables itself, indicate the variables are fine, and then we just like.
well, your choice of variables should be influenced by your theory of change and theory. So if you think those variables are important, can't really go changing them because it doesn't provide a match balance. If changing the specification still didn't work, then you might have to try and expand your control sample by sampling from a wider area. If that doesn't work, you might have to reconsider your study. I don't know. Let's hope that doesn't happen.
Okay. Because also it's like a nearest match, right? It's not really like an exact match, so there is at some point that the matching will occur. It's just like you relax your criteria.
Yeah.
Like your one standard deviation can become two standard deviation, but then it's like not so good.
Yes.
Of a match, so like where do you draw the line?
Yeah. I don't know, to be honest. I think that's something you would have to
And so
decide.
also a robustness check that you have to do at the end, that you try to compare different control group.
I didn't compare a different control group,
No,
but that could be a robustness check. Yeah.
okay.
Yeah.
You ended up sampling from the comparison, you were by taking just like the 1 pixel per 150 meters or something.
I did, yeah.
Yeah, so like you're using small share of potential data as a comparison group. But I guess a statistical draw, you can resample that a bunch of times.
Yeah. You're right.
Theoretical reason like that.
Yeah.
Particular sampling group was better than the other random draw.
Yeah. Oh, excuse me? Excuse me? The thing's not working again. Okay, thank you. Okay, so we've got our match data, yeah? The next thing that we're going to do, this calls back to my distinction between the unit of observation and the unit of analysis earlier, is that we're not going to stick with pixel level outcomes. We're going to aggregate the data to the sample. And so we're going to count. Gosh. Well, never mind. We're going to count the number of observations in each sample I wanted to go back, but it's just being, I think it's losing the signal or something. Okay. Yeah, basically we're going to count the number of pixels that were deforested each year in the treated and the control sample. And that will give us a continuous outcome measure, which is much more friendly and I think more kind of easily interpretable than a binary. And it basically says, out of this subsample of pixels from my offset, which is about 4%, how many were deforested each year between 2001 and 2019? And then we run our regressions on that. So I'm actually a slide ahead. But if you run the next bit of code, which is 1F, from lines 364 to 375, it will do that aggregation for you. And then you can see on your screens what it looks like. So instead of having a data set that's 5,700 observations, we've got a data set that's now 38 entries. And for the treated and the control sample, it counts the number of deforested pixels each year. And then if we, great, it's working again. Are we up to date? Have we done that? And then the next step is that we need to do some preparation for the regressions.
Explain what this data set is again, the annual deforestation.
Yeah. So you can see there's a column that's, what's it called? Trees or something. Yeah, so it's the binary. And then the years and the year. And that represents between 2001 and 2002. Okay. And then the annual deforestation is the count of pixels within the sample of 2,800 that were deforested in that year.
They should all sum up to 2,860.
No, because some pixels weren't deforested. Okay. Unless there's zero there, that's. Okay. No, but there's a year that's, is there a year that's zero?
Yeah.
Okay.
Well,
Okay, so that's fine. So it won't sum up to 2,800 because many of those pixels are still forest.
so is that what we're seeing with the 38 observations of 3 variables?
Mm-hmm.
So 38 total pixels of the 2000.
No, the 38 is the year between 2001 and 2019, replicated twice because there's values for the treated and the control. So if you open the data frame and look at the year column represents the years between 2001 and 2019, and you'll see that those numbers are replicated twice. The treated column denotes whether it's the control or the treated sample. And then the annual deforestation is the count of pixels within our sample, within our match sample that were deforested that year. So, for example, the first row says 7. So that means 7 comparison pixels were deforested in 2001. There you go. Fun fact for a pub quiz. Okay, so now we're going to start preparing the data for the regressions. So we need to add a time indicator. Remember, currently the data includes years before and after treatment. And so we need to add an indicator saying whether that year is before or after treatment. So that's what this offset and Kerner was protected in 2011. So all years before 2011 are going to be assigned a 0, and 2011 and after is going to be assigned a 1. So that's lines 386 to 396. And finally, in this stage, we're going to transform the outcome variable. Because this is count data, and there's lots of zeros, less so for this offset, but there's another one where there's lots of years where there's no deforestation in the sample. So it's zero inflated and it's like skewed to low levels. So we're going to apply a log +1 transformation. And you could argue about that. Like there's other transformations that I could have used, like the inverse hyperbolic sign. But I didn't know about that then, so I just used this one. And we have to add 1 because of those 0 values, because if you take a log of 0, it freaks out. So we've done that, yeah? Right. Great. Now the data is ready for the fun stuff. So first of all, we need to test one of the key assumptions of difference in differences, which is the parallel pre-trends. If any of you were in the session before lunch, you would have heard all about this. But just in case you weren't, basically, this is a little schematic that I made to explain it to myself, and then I thought it was actually quite useful. Basically, difference in differences is saying that we can use outcomes in the comparison after treatment to infer what would have happened in the offset if it hadn't been treated. Now, a really important assumption to that is that the two follow similar trends. And so we test that assumption in the pre-intervention period, because that's the only time that we have that we can do that, basically. Because if the two samples are not following similar trends in the first period before treatment, why on earth would we expect that they would still follow similar trends in the second periods? We wouldn't. So that's what we're assessing here. So to do that, we have to subset the data to leave only the years before treatment. So only the observations where year is less than 11. So if you run the lines, section 2A, lines 422 to 426, you can test, no, oh, hang on, I haven't run the previous bit. So that will subset the data. And then you can run the subsequent regression, which is this one. So this very simply is saying, predicting the log transform deforestation based on the year, based on whether it's on the treated or the control sample, and the interaction between the two. And then when you do summary of the results, you will get a table that looks like this. Have you all got that? And then this is the coefficient of interest. This is saying, does the relationship between deforestation and year differ depending on whether the observation is in the treated or the control sample? And we find that it doesn't, which is great. Parallel trends assumption ticked. But importantly, it also says that there's no relationship between deforestation and year at all. So, which is actually not that unusual for deforestation, because it's shows high interannual variability. So basically, neither the control nor the treated sample show any relationship with year. No, show any deforestation trends over time, which you can see here. That's not the case for all of the offsets. Some of them do. And remember, I had remember I had 4 offsets. One of them didn't meet the parallel trends assumption. So I couldn't run the difference in differences analysis on that offset. But I did include it in the fixed effects regression. Because the relationship with parallel trends, I think, is a bit hazy for fixed effects regressions. But I also ran the fixed effects without that one, just in case. So
Yeah, just going back, one other thing that you might do is include all of the pre-intervention data in your mapping in the first place. So in this case,
Yes.
it wouldn't matter because as you've already shown the balance just matched on the other variables. But if you end up in a world in which they're imbalanced like that, you might go back to your matching stage and include those trends and matching.
yeah.
in the matching stage.
I've just realized the time, so I'm gonna have to speed up a little bit here.
One other question,
Yeah.
I was just wondering, what is all, when the parallel trends are evaluated? They're evaluated on the time interval, I guess, right?
What do you mean, sorry?
Meaning that 2 points, if you have 2 time series, they could have very similar value at 2 points, but diverge in the middle. So how the difference between the 2 is evaluated?
So that's annual, the outcome is measured annually.
Okay,
And I suppose that if for the first 3 years there was a significant trend, and then the next it was no trend, and then the final 3 years of the pre-intervention period there was a trend,
Yeah.
then it could show up as no trend overall over that period. That's possible. It just depends on what years you choose, I suppose. Right, so we passed the parallel trends test. Now we can run the DID, the difference in difference. So please run lines 459 to 464. And you will get a results table that looks like this. So this is for the full time series of data, the whole 19 years. And the coefficient of interest is this one here. And this reflects the effect of being in the offset in the years after protection on the log transformed count of deforestation and its significance, which is really great. This doesn't make any sense, really, just like it is. So we need to transform it to something that makes sense, which is the next bit of code, which is essentially undoing the transformation that we did before. So if you run that next section of code, oh, you should get a result that is minus 0.958, blah, blah, blah. And you'll get a confidence interval as well. And basically that means that protection of the offset reduced deforestation by an average of 96% per year with those confidence intervals, which is huge, right? Like that's one of the biggest effect sizes that a meta-analysis of deforestation policies found, and it's done by a private company. I'm just going to skip over this, but we used that percentage to convert observed deforestation in the offset to counterfactual levels. And then we took the difference between the counterfactual deforestation and the observed deforestation to estimate, and the difference is the amount that's been prevented, which equates to 1,922 hectares just in that one Ankara offset, which is why I chose it the example, because it's the one with the biggest effect. And those are the confidence intervals. And that equates to 79% of the forest that was cleared at the mine sites. But now, in the last 5 minutes, we're going to check whether these results are crap. We're going to check whether they're whether they're just a kind of product of the modeling specifications that I used. So the next bit of code includes a very chunky function that my colleague Sébastien Despireau made to run the robustness checks. And there's two functions. One is called the parameters loop, and the next one, you probably can't see it because it's really far down, is called the covariates loop, I think. So run that, because it will take a few minutes. If you just press the green triangle in the top right corner, it will run the whole thing. And while it's running, I'll tell you what it's doing. So basically, it specifies a combination of different parameters. So the parameters are the distance, the statistical distance measure with these options. So far we just run it for one set of parameters, right? This loop will produce results for, your loop's just going to test 16 different specifications with different parameters, right? But the full thing tests 116. So your loop tests, what does it test? It tests two different caliper values, so setting it at 0.25 and 0.5. It tests matching with replacement or not. It tests using a Mahalanobis distance measure compared to the propensity score, which is the GLM. It tests using a ratio of 1 control to treated or 5 controls to treated. And it tests every possible combination of those, which results in 16. And then it will run the matching, it will run the parallel trends test, and it will run the difference and differences. And it will output a table. Do I have that? Yeah. It will output a table that looks like this. And it will also, so the first column is the coefficient from the DID. The second is the standard error. Then it will show you how many treated pixels were unmatched. Remember, we want to match all of them. So this is no good. So we don't really want to get rid of like over a tenth of the data. It will give you the average standardized mean difference. So this is a measure of covariate balance. It will tell you whether the parallel trends assumption was met. And it will tell you what specifications were used. Because this is just changing the parameters, there's no additional covariates added. And then there's various different ways you can visualize these results. So in our paper, we did it like this. Each point represents the raw estimate from one of the specifications, and the bars are the confidence intervals. The ones that are shaded a light color. Pardon? No, whether they're below, whether the line is below this indicates significance. The light color indicates whether the specification is what we call a posteriori valid. So whether it's a valid model or not. Because remember, if some of the specification didn't meet the parallel trends, then we don't really want to listen to what it's saying because they might be rubbish. Likewise, if they didn't match lots of treated pixels, we also don't want to pay too much attention to the results. And in our paper, we set kind of rules. We said that if there's no parallel trends, if the mean balance, covariate balance was above a certain value, and if a certain percentage of treated units were unmatched, then we're going to consider that not valid. And those are shown in the paler colors. And the main specification that we just run is shown in black. And so what you can see here is for Ankarana, almost all of those different specifications showed a significant reduction in deforestation, and most of them are of a really similar magnitude. Kind of the same for the conservation zone. This is the one we couldn't assess because it didn't meet the parallel trends. And most of the other specifications also didn't meet parallel trends, which probably means there's something quite unique about this place. This offset, we didn't find a significant effect of protection, and so did the majority of specifications. So these results were amazing. They made me very happy. And also, we did a few other tests in the paper. So we're not going to do it now because we ran out of time, but in the fixed effects model, we tested using fixed effects versus random effects. We dropped out each year of the analysis sequentially to see if the results were overly influenced by outcomes in a specific year. The results were still robust. Then in that independent replication analysis, they tried using different data, the tropical moist forest product. The results were still robust. There was still a significant reduction in deforestation, but the magnitude was lower than I found. They tried a different transformation of the outcome variable, still robust. They dealt with the errors much better than I dealt with the errors, still robust. The only thing the results weren't robust to was using a Poisson regression. And I'm not really sure why, but the economists who did it were not surprised. And they said that some Poisson regressions bit better. So, yeah. Now, I don't know if is your loop finished running?
Yeah.
Yours has. Yeah, it takes a few minutes.
No.
Yeah.
Okay.
So the next loop tests adding the additional covariates into the model.
Okay, for the match itself.
Exactly, yeah. So it holds the parameters, the distance measure and the other parameters constant, and it tests the effects of adding in those other variables into the model.
I have a question there, like, do you also see if these variables are correlated, should you check it?
Yes, I did check it.
Yeah.
Yes, I can't remember, sorry.
But we should not include if there's a high correlation between these variables, or we should include only one of them?
Probably only one, because like I said, matching becomes more difficult than what So if two are highly correlated, then you're going to be getting the same information from both, and perhaps you probably don't need both.
A question on the policy level.
Yeah.
Who is doing most of the deforestation outside of the protected zones? Could the mining company be participating in deforestation?
No, but just it could be an indirect effect of the mine, because the mine brought people into the region. That could have increased demand for food and land, which could have elevated pressure. The people doing the deforestation, both in the protected area and outside, are like local subsistence farmers.
No.
So this is a really good question, because yes, these offsets turned out to be effective at slowing deforestation. The aim of the offset was to compensate for impacts from a major mine that's producing a product for export. But that compensation was achieved by stopping very poor local people from pursuing their livelihoods. And the mine knew that, and they did implement kind of measures to try and mitigate those negative impacts on people. So it had alternative livelihood projects, etc. But there's another really important study that should go hand in hand with this, that was done in 2016 by Cécile Bidot, and she interviewed people living around the offsets and asked them what was the impact of this new conservation regime on their. Oh no, about the alternative livelihood schemes and the conservation restrictions implemented by the mine. And people said that it wasn't enough to compensate for their loss of access to the forest, and that the people who lost out the most were the least able to access the compensation projects. So yeah, basically it was really very poor local people that bore the costs of this offsetting to provide metals that are used all over the world. Yeah, I think we will wrap up now. Oh yeah, sure.
Just, I guess, a question more about the, what they actually did to conserve, I mean, so they established these new conservation areas, and then did they like build ranger stations and hire staff to keep people out, I guess, how did they, from the actual like
Yeah.
implementation side, like what activities did they do that allowed it to be so successful?
Yeah, they did quite a few different things. They've established and supported village forest management committees. With their monitoring controls and things. They were just a very visible presence in a way that like protects area authorities aren't. Everyone knew the rules, which was also quite rare.
Yeah.
Yeah, I think mostly just supporting the work of existing NGOs. And
So it's not a big form like they're
No.
armed militia.
no,
But I mean, it's like people, groups do that, right?
Yeah.
Design conservation, like they do that in Brazil. And
Yeah.
What middle is successful.
Another thing is that one of those offsets is actually within the boundaries of the mine concession, over which the mine basically has ultimate power. And parts, access is just so restricted. People do still get in and use the forest, but like it's very clear that this is the mine's area.
Maybe I'll catch you after, just it just seems very, but the efficacy is surprising.
It's surprising. Yeah. But anyway, thank you all for coming. I hope you learned something. You can play with that data and adapt it and use it how you like.